Welcome to this lecture of elements of mechanical vibrations. Today's lecture is going to be devoted to obtaining response to harmonic excitation. Okay, so, for a vibratory system, the excitation that we discussed till date is in the form of initial perturbation or initial excitation at t is equal to 0. That is what by using initial displacement and initial velocity, these two conditions we considered this. So, an example of that was like a step dip to any vibratory system, which either generates an instantaneous initial displacement or initial velocity, depending upon the example or the case in question. So, for example, if this is modeled like a spring mass system, exactly at this particular instant of time there is an initial displacement condition that we typically introduce, and then because of these initial condition, what is the response of the vibratory system, that is what we considered. So, this is like initial excitation at t is equal to 0, and that generates the response. The other type of excitation that we discussed a few lectures back was arbitrary excitation. Now, that arbitrary excitation is not really a sort of an initial condition at t is equal to 0, but it persists for certain duration of time. So, this time is not infinitesimally small, it persists for a reasonable period of time, and it may or may not be captured using some mathematical form, and we discussed how numerical approach can help us evaluate the response to such an arbitrary excitation. Essentially, this arbitrary excitation case was actually stripped into the case of initial perturbation by considering series of such initial excitations through the impulses. Okay. So, this was the second type of excitation that we discussed for a vibratory system, wherein short duration transient excitation like a blast load on the concrete tank or any other mechanical system like a hammer, impact hammer, which is a vibratory system, the excitation could be of transient or arbitrary type. The most important part is that this time is finite and the excitation does not really repeat. So, it is different from the initial excitation case, but it is definitely different than the other common types of excitation, mainly the excitation that is sustained. For example, some of the examples that we considered were that of a tappet valve mechanism in an IC engine, wherein this as a vibratory system was excited through the cam, and as the cam rotates, the tappet valve will be pushed up and down in a fashion which cannot be defined through this kind of a arbitrary transient excitation. Similarly, we considered the case of a wind turbine nacelle rotor, wherein the rotation of these blades generate again excitation which is sustained, and in this particular case will be in the form of a harmonic excitation because of the residual unbalance in the blade system. So, such a vibratory system, when it is subjected to excitation force or excitation displacement, which is time varying and sustained, we need to now look at how the response to such excitation of a simple vibratory system can be estimated or found. Okay. So, I hope it is clear now, the initial excitation case, the arbitrary or transient excitation case, and now finally, we are migrating to a more realistic and more commonly observed excitation source, which is a a time dependent sustained excitation function. Now, out of those sustained excitation function, the most common one and the most easier to address is the harmonic one. Okay. So, something which is given by f sin omega t or f cos omega t. So, this is so if this bladed rotor spins at a speed of, let us say, omega radians per second, because we know that the unbalance rotates with the same frequency as the rotation frequency, and therefore, it varies harmonically with the same frequency omega as the rotational frequency. And here f is you all know that is given by me omega square, the unbalance force. So, the excitation force f, whose magnitude is this, and it fluctuates with the frequency of omega, which is the rotational frequency in this particular case. The excitation function f of t, the time dependent forcing function, is given by f sin omega t, and it is typically called as an external excitation because neither the amplitude of force nor its frequency has anything to do with the system in question. So, system parameters like k, m, they are independent of or the excitation function is independent of those parameters, and is truly an external excitation. And so, the job now is to figure out the way we found expressions for finding out x of t for as a vibratory response of such kind of a vibratory system. Here also we are interested in finding out what is the response x of t of this vibratory system when it is subjected to external forcing function given by something like this, a harmonic excitation function. Typically, you might as well find excitation function which may not be exactly harmonic, right. So, for example, in an IC engine, the excitation torque to the crankshaft could be like this, although it will repeat perfectly after a certain period of time depending upon whether the engine is 2 stroke or 4 stroke. This excitation torque will repeat itself, and then the excitation is still a sustained excitation, but we cannot or may not be able to use this expression to represent the external force or torque on the system. So, then we resort to something else, and that also is a part of discussion in this response to external sustained forcing function. But we shall take that up after we have extensively explored the response to harmonic excitation. So, this type of excitation because it repeats a certain period of time is periodic excitation, which is going to be discussed and dealt with once we are done with the excitation which is harmonic in nature, because of the fact that getting expressions, getting the response to harmonic excitation case is mathematically straightforward and more simpler, and the response to periodic excitation is a natural extension, and we shall see how we can use all what we learn through this response to harmonic excitation to get the response to periodic excitation. So, that is the topic of discussion in next few lectures. Okay, so, when we say response to harmonic excitation, the right hand side which used to be set to 0 in our earlier discussion of the governing equation of motion for a single degree of freedom system, we usually keep the right hand side term equal to 0, and then started with response to initial condition. We extended that to arbitrary excitation, keeping right hand side equal to 0, essentially 0 in the solution process. In this case, the right hand side is non-zero, and that can take the form in different ways, but one of the common form as we discussed can be f cos or f sin omega t. Okay. Now, the examples are like an electric motor which is spinning at certain speed supported on these bearings, and we discussed this example which can be modeled in a simple fashion like a simple shaft, a flexible shaft and a rigid rotor at the a disc at the center of the span and the bearings offering a simple support, which itself can be modeled like a spring mass system. And then if that is modeled like a spring mass system, if we consider the vibration in the horizontal plane, then because of the stiffness of the shaft, the rotor can be assumed, or a disc can be assumed to be a lumped mass here. This is representing the shaft stiffness, okay, and maybe some damping can be assumed in the shaft material. And then this becomes again a single degree of freedom system, which will be subjected to a forcing function because of the unbalance created by this residual unbalanced mass. Okay. So, all practical rotors cannot be balanced to 0, it will always have some residual unbalance, and that unbalance will create excitation to the shaft rotor system or a rotor bearing system, so to say, and that f of t can be modeled like a harmonic forcing function f cos omega t. Now, there are ways in which this forcing function is represented. It is, as I said, can be represented as f cos or f naught cos omega t. F naught is the amplitude of the force. Now, that f naught can be any value. In a rotating unbalanced case, it can have a numeric value or an amplitude equal to m e omega square. E is the eccentricity of the unbalanced mass, this is an unbalanced mass, and that amplitude can be given or obtained numerically using these terms. So, it will be fixed for a given operating speed. The other alternate way is to represent f cos or f naught cos omega t as a real part of a complex forcing function which is given by f naught e to the power j omega t, because we know that this part can be written as f naught cos omega t plus j sin omega t. And if I take the real part of this forcing function, I get back this particular expression. Now, either ways you can solve the equation either from the first or from the second equivalent expression, but for the sake of mathematical simplicity, we will use the second of the two equations. Okay. All right. Before we do that, a small assumption involved here, as we already have discussed, that most of our vibratory systems vibrate with small amplitude of vibration. So, we assume small amplitudes of vibration, and it also has implication in another assumption that the system is linear. Okay. So, systems are typically considered linear when the amplitudes are small enough, so that your force restoring force to displacement or vibratory displacement relationship is linear. So, your constants m, k and c, these elements of vibratory system are having constant coefficient values k, m and c. As long as they are constants, the governing equation of motion is linear. Okay. So, with that assumption of a linear system, linear vibratory system, sorry. So, linear vibratory system has a property that if you move this linear vibratory system with an excitation force having a period capital T, the response is expected to be at the same period of oscillation, right. So, when the excitation force f of t has excitation or repetition rate and the frequency omega, then your response x of t will also have the response which is given by omega. Okay. Of course, this will get slightly modified, we will discuss that in detail, and of course, the response will be with some amplitude, we do not know what that amplitude is, but definitely one thing is for sure that for a linear vibratory system like what we are discussing, if you excite it with the frequency omega, the response will also be with the same frequency, that is omega. Now, so the assumption here is that we shall since we have decided to stick to complex notation, the assumed solution. Okay. So, we assume the solution the way we have also done it in a free vibration case. Assume the solution of this equation to be given by an unknown amplitude and frequency, of course, for a linear system the same frequency as the frequency of excitation. So, we assume complex harmonic response capital X e to the power j omega t. Okay. So, that is an assumption. With this assumed response we will continue further. So, my equation of motion now for a complex response function x of t, I shall start like this. The forcing function is also complex, and so now if I substitute, if I assume the solution to be x e to the power j omega t, the velocity x dot which I am going to use when I am replacing these response variables is going to be j omega x e to the power j omega t. Similarly, the second derivative would be minus omega square capital X e to the power j omega t. Okay. So, these are the response variables x, x dot, x double dot, the time derivatives of the response variable x. I will now replace them in the governing equation of motion here. So, what will I get? Minus m, if I substitute x double dot from here, minus m omega square capital X. Now, I am going to get e to the power j omega t for all the three terms. So, I will keep them out, and then what will happen here plus j omega j c omega capital X e to the power j omega t is a common factor which I will take outside, and then this k and x is capital X. So, all the terms involve e to the power j omega t, and that is a common factor here, and then I have the forcing function on the right hand side as it is. If I assume some solution in the harmonic expression like x cos omega t or whatever, I will eventually get the same result as I am getting with the complex notation, but this helps me have some simplicity in terms of mathematical manipulations, because otherwise some terms will have cosine, some will have sine, and so on and so forth. This looks little more convenient to use, and that is why we are pursuing with the complex notation. Now, if this is the case, can I write capital X here equal to f over k minus m omega square plus j c omega, right. So, e power j omega t cancels out and capital X can be written like this. So, this is your what are you getting from this expression? You are getting essentially you are getting basically the response amplitude, okay, the amplitude with which the vibratory mass is going to oscillate. Okay. For a given magnitude of force F and for given frequency omega. Okay. K, M, C are the system parameters which are already known. Based on the amplitude of F and the frequency omega, this capital X will get found. So, if I know this X, I have already obtained the response capital X e to the power j omega t, that is my response, is not it, because capital X is known, omega is known. So, I have the response already known in terms of time, but it makes sense to sort of reformulate this expression. The denominator is a complex quantity. So, we are going to now slightly modify this expression for better use, and we in the process can get non-dimensional expression, okay, dimensionless expression of the response. Okay. What do? We multiply and divide this by its complex conjugate. Is not it? And you just simplify this, what will you get? F, now I will take F out. Now here there are two quantities, one real quantity which is this, and then there is an imaginary quantity C omega, and the denominator changes to K minus M omega square. Is not it? I can write the same, this expression so I will write capital X to be equal to F, okay, and can I write this A minus JB as what? Square root of A square plus B square, right. So, I can write this as K minus M omega square whole square plus C omega square e to the power minus j phi, some angle. Okay. So, what is that phi angle? That is going to be the tan inverse of B minus A, sorry, B by A. Now, what that B is, right, what is that B is C omega over K minus M omega square, and that this negative sign I am already accounted for in writing it as e to the power minus j phi. We know this from our complex algebra. So, K minus M omega square whole square plus C omega square. Now, what? It is quite clear from this. If I move over to this expression that I wrote, it was F square root of K minus M omega square whole square plus C omega square E over minus j phi over K minus M omega square plus C omega square, is not it? That is what we got. So, I will rewrite this as F. Now, you can see that this is going to be square root of K minus M omega square whole square plus C omega square E over minus j phi, and I will take this K out from the denominator. Okay. what do I get? If I take k out of this, in the numerator I can take that k, and in this denominator 1 minus m omega square over k whole square plus c omega over k square, is it not? Now, f over k will be what? You have a simple single degree of freedom vibratory system, and you are applying a force F which is time dependent, or maybe I can write this as F naught e to the power j omega t. So, I forgot to add this F naught, which is basically the amplitude of the harmonic forcing function. So, suppose there is no frequency, I mean this force is static in the sense that it is not fluctuating with any frequency, it is a static load. So, what will be F naught by k? It means that if I apply, just like gravity, if I apply a constant force, this mass will deflect by delta, right, static deflection, right. Yeah. So, that delta is going to be force divided by the stiffness offered by the spring, that is going to be its deflection. So, that is going to be called as zero frequency deflection. Sometimes in literature they call it as static deflection. Static deflection in the sense that if the force is a static one, the amount of deflection that the mass undergoes under the action of that F naught force is going to be x s t, zero frequency deflection. Zero frequency meaning generally this F naught f of t is a harmonic or a fluctuating force. If that fluctuation goes off, it is static, then the mass will deflect by deflection equal to x s t. Now, what I do is this numerator F naught by k, which I have now called as zero frequency deflection or static deflection, I will take it on the right hand left hand side. So, I will now take this as a ratio, okay, and what I will make few more simplification in the denominator. What is m omega square over k? This is going to be omega over omega n whole square, because k over m is omega n square. So, I will call this ratio as R, which is very typically referred to in literature in all your textbooks. R is the frequency ratio, okay. Frequency ratio, why? Because in the numerator you have an excitation frequency, in the denominator you have natural frequency. So, it is a ratio of two frequencies, one impressed external excitation forcing frequency, and in the denominator you have natural undamped natural frequency of the system. And what is C omega over k in the second term under the square root sign in the denominator? I can write this as C over Cc, and Cc here in the numerator omega over k, which I will replace. Now, this Cc will be or C over Cc I will replace with our parameter, normalized damping or a damping factor. What is Cc? Critical damping coefficient, which has the value equal to 2 m omega n, isn't it? And I have omega here and k in the denominator. Again this k m over k is nothing but 1 over omega n square, which means that this can be written as 2 zeta r, where r again is omega over omega n. So, you can see that this entire ratio will turn out to be 2 zeta into r. So, our C omega over k is now going to be replaced in the expression by this and by this. So, finally, I have 1 over square root of 1 minus r square whole square plus 2 zeta r whole square e over minus j phi. Right. Okay. Which actually means that the right hand side is all dimensionless. All parameters that you notice here are all dimensionless quantities. Zeta is dimensionless damping, r is dimensionless speed or excitation frequency. It is non-dimensionalized with respect to the constant natural frequency of the system. Okay. The left hand side a term is also an amplitude ratio. It is normalized response. The actual response amplitude is capital X, but we have normalized it with respect to 0 frequency deflection. Okay. So, in a sense it is a normalized dynamic vibration response. We shall discuss more about this ratio in the next slide. But what we get actually as capital X is XST or 0 frequency deflection, static deflection 1 over the same ratio that we have used here 2 zeta r whole square e over minus j phi. This is an amplitude. The actual dynamic response, because we are interested in knowing what is the response at any instant of time t. Okay, when it is subjected to a harmonic forcing function, I mathematically would like to get an expression that defines the response at any instant of time. That is the dynamic response. What you have got here is the amplitude of that response. Okay, it is a single quantity. What will be x of t? Because we have assumed the solution x of t to be what? Capital X e over j omega t. So, therefore, if I replace this capital X, I basically have this x s t e over minus j phi over square root of 1 minus r square whole square plus 2 zeta r whole square. This is my capital X e over j omega t is basically the harmonic force, harmonic function. So, this is its amplitude and that is the harmonic time function. So, if the force is harmonically varying like this, right, the response will follow. Now, that response will be still harmonic with frequency omega. So, maybe I will show the response maybe like this. Of course, they will have the same time period. So, that part we are going to discuss very shortly, but the point is this is its amplitude capital X, right. This amplitude of the force was f naught. The time period of forcing function capital T is 2 pi over omega, and for the response, okay. So, for the response, if this response goes up like that, then this response will also have a time period capital T, which is going to be 2 pi over omega. Okay. So, what I will do is that I will rewrite this expression in a more common standard form, and that is going to be xst over square root of 1 minus r square whole square plus 2 zeta r whole square e over j omega t minus phi. I'll club and the two exponential terms together, and that is how we get it. Now, x of t with our initial definition here is a complex quantity. So, if I want to write the real part of it, which is the response in maybe in the horizontal plane or a horizontal direction, I can write x of t as x s t again with the same square root sign term cos omega t minus phi. So, it's like taking the real part of this expression, okay. But you can as well keep using this expression which defines the response of a single degree of freedom vibratory system to a harmonic forcing function with constant amplitude capital F naught, okay. X s t we refer to as F naught over k. Okay. Now, there are few things which will be clarified shortly. This is definitely not the total response, okay. Keep that in mind, because we have solved this equation for the right hand side forcing function. However, the response is also contributed by the solution of the homogeneous part of the total equation, mx double dot plus cx dot plus kx equal to let us say f naught e over e to the power j omega t. We have got the particular integral part of the solution. The solution to this homogeneous part of the equation is not included. The total response of the system is going to be x h t plus x p t. Now, what we have got here is actually the response to the right hand side forcing function, but the solution of this homogeneous part mx double dot plus cx dot plus kx equal to 0 has to be also included to complete the response, okay. So, the response expression will be complete by adding this response to the response that we have already derived. Now, can you tell me what will be the response x h t? So, which I will add to this solution. You remember solution to mx double dot plus cx dot plus kx equal to 0. What was x of t that we got for this? It was what? Capital X. Now, that capital X is also not to be confused with this x, okay. So, x h e over j minus j what? Right. So, this was minus zeta omega n t, is not it, exponentially decaying quantity, right, with the amplitude x h which was again a function of initial displacement, initial velocity and other parameters of the system. What was it multiplied with? Now, please refer to the expressions that we derived and we discussed in a free vibration case, because we are still getting the response to this part of the solution. So, x h, if you remember, was a function, was a quite a long expression, but was a function of initial displacement, initial velocity, zeta, omega n and omega d, right. Similarly, this initial phase lag which is appearing in this expression here is again a function of these parameters, right. So, the total solution, now I should use the total solution is going to be this. It is not only this part, okay. This part is part of the total solution, although in practice we do not really worry about this part of the total solution, okay. Most of the times when the response to steady state excitation force is required to be found, we focus mainly on the first part of the solution, that is to steady state forcing function on the right hand side, and usually this has relatively less relevance, or in fact is ignored altogether in assessing the forced vibration response. And what could be the reason for it? Yeah, the reason is this exponentially decaying quantity ensures that within a few cycles, depending upon the strength of zeta, the solution, this part of the solution, okay, dies out quickly. So, in a way within no time you are actually left with only the response of the first term, that is the steady state solution we call it. So, this part dies down quickly, and what is sustained or remains is the solution, which is this xp, okay. And therefore, in general in practice we are all the time concerned about this value rather than this particular value, okay, because that amplitude quickly dies down because of the presence of damping in the system. If you really do not have damping, enough damping, if the damping is almost 0, then you need to consider the second part of the solution. Usually in practice most of our mechanical vibratory system does have reasonable damping, which causes the decay of the second part of the solution quickly and quick enough, so that what matters is the solution defined by this expression, okay. Okay. Now, we shall come back to this discussion shortly. So, if I want to show this response, I think it would be interestingly shown in this particular graph itself. So, if I plot now the total solution, okay, if I want to plot the entire solution, which is like x of t as a function of time, I could get the response something like that. So, what is happening is, in this initial part of the total response, the total solution is contributed by both the steady state part as well as the transient part, initial part, okay. So, in the initial period of the solution, both xh as well as xp, okay, that is this xp and xh, which was given by this expression, both of them contribute, and the total response is a combination of both of them together. That is why you see some perturbations like that. Whereas, after a few cycles only this steady state solution persists, and what you see is a constant amplitude response, where this x is what this x that we have got here, okay. it is only this x that remains, and the initial part, which is like a mix of both responses, will appear. Okay. How long this period remains is again dependent on the value of zeta. If you have a large zeta more than 0.1, within couple of cycles you will find that this completely settles down. Okay. If you have zeta which is like 0.01, maybe few more cycles before the contribution from the second term vanishes, right. So, this is the total x of t. Okay. Now, because this part of the total solution is much smaller compared to what we are now interested in getting later as a stabilized or a settled down response, the first part is ignored. That is what I wanted to highlight here. Okay. So, finally, we have this expression. It is your job probably to also replace those quantities that we wrote in the expression of phi, which is c omega over k minus m omega square. So, if you rearrange all these terms, take the non-dimensional ratios like r and zeta, you can definitely get this expression for the phase. Now, this phase angle phi is different than the phase angle phi I that we have been writing for a free vibration case. In a free vibration case, we wrote capital X e to the power minus zeta omega n t cos of omega dt minus phi I, where this phi I was written as initial phase lag. Now, that phi I is going to be different than this phi, the phase. Okay. This initial phase lag actually is the phase that represents what is the angle made with respect to time t is equal to 0 of the first peak there. Okay. So, this phase lag you remember was equal to 0 when the system was subjected to initial displacement, no initial velocity. If it is initial velocity, no initial displacement, it was 90 degrees, right. So, when there was initial displacement, the phase angle was 0. So, this is how the response was like a cosine function. If it is initial velocity which is imparted, it will cause sinusoidal response, and therefore, the initial phase lag was 90 degrees. Okay. If it is mix of them, then it will lie somewhere in between 0 and pi by 2. So, the point here is that this phase lag should not be confused with the phase angle phi that we have gotten here. That we shall discuss, of course, what is the meaning of this phi phase angle. Okay. Now, now having obtained this ratio x over xst, that is the normalized response of this response amplitude of the system capital X. The xst is the static deflection or zero frequency deflection, which is as we discussed is f naught over k, and small r is the frequency ratio, forcing frequency ratio, the ratio of the forcing frequency omega and the natural frequency of the vibratory system. Now, this ratio x over xst is called as the dynamic magnification factor or a dynamic magnifier. It actually represents a factor by which the displacement amplitude due to the same static force F naught gets multiplied, mostly amplified, and reflects the effect of frequency of applied force. Why? Because suppose you have this vibratory system and you are subjecting it to a force, okay, which is fluctuating with a frequency omega. If this omega is 0, the corresponding response is going to be xst. But if this omega is non-zero, you get a response which is capital X. Okay. So, when frequency 0 is our reference amplitude or reference deflection or response. So, if I take the ratio x over xst, it represents the factor by which the response due to no frequency or 0 frequency or just a static deflection gets amplified when frequency changes from 0 to some non-zero value. Okay. So, which means that if instead of a static force, if I cause that force to fluctuate and vary with certain frequency acting on the vibratory system, the amplitude changes from xst to x, okay. And you will find that in general that ratio is more than 1, of course, barring certain frequency range, and therefore, it is actually capturing the effect of frequency of excitation, right, because it is referred with respect to the case when the frequency is 0 to a case where the frequency is non-zero. So, it of course obviously will manifest the effect of a fluctuating force, a dynamic force on the vibratory response of the system. Okay. So, what has been done now is we shall have a look at how this ratio, okay, x over xst, this ratio, because x is going to fluctuate, is going to vary with different frequency omega, it makes sense to check how this ratio varies as I keep changing the value of omega from 0 onwards. Okay. Okay, but before I do that and discuss that, a more very important assumption involved here is that this force F naught, okay, which we are assuming is a constant value. That means, keeping F naught as a constant value, if I simply change the frequency, okay, what will be the effect on the response amplitude capital X. So, the examples that we considered earlier of a rotating shaft actually will not apply here. The reason this is that that the force amplitude itself is a function of frequency. So, the amplitude will keep on changing, but as a hypothetical case, let us assume what response variation we get by assuming for the time being F naught being constant. We are definitely going to consider the case where F naught is going to be a function of frequency of rotation. So, if I plot this x over xst with the frequency ratio r, okay, then the variation of this ratio, dynamic magnifier, we have defined as changes with respect to the frequency ratio r for different values of damping. The damping in our system C is normalized again with the critical damping coefficient, and the value of the damping factor is used. So, for a given damping factor value here, if I simply vary the value of r, the variation of x over xst, the dynamic magnifier can be observed. Okay. What you observe, let us say take any particular value of zeta, let us say 0.15. What you notice, the amplitude will keep on rising, it will reach its peak and then come down as the frequency ratio changes. And what does this 1 indicate? The value of 1 indicate that the response is equal to the static deflection or a 0 frequency deflection. Obviously, all the graphs will start from 1. So, now taking this as a base, okay, if this is the response due to a force which is constant for a static force, what change in the response happens when the force is fluctuating or is having certain frequency of repetition. It has a repetition rate omega. So, what is being observed here is that at all of these r values, the actual amplitude capital X is here 2 times the static deflection, here 3 times the static deflection, here maybe 3.7 times the static deflection, which means that there is an amplification happening in the response of the system. Okay. So, even if the excitation frequency is let us say 0.2 or so, if you keep on increasing the frequency ratio to a higher value, somewhere around a value of 1, which means that the excitation frequency over natural frequency, which in our case is written as R, as it approaches 1 or becomes close to 1, which actually means that the excitation frequency is same as the natural frequency of the system, there is an amplification in the response, which is we all know that is referred to as resonance. Okay. So, when the frequency nears the natural frequency, there is an amplification in the response amplitude, and then the system vibrates with very large amplitudes of vibration. You remember that the typical material damping is of the order of less than 0.01, in fact 0.02 or so. So, the peak is going to be somewhere up there, that means it is going to be many tens of value. So, x over xst, which you are seeing here up to 3.6 or 7 or 8 or whatever, that can actually approach a value more than 50, which means that the 0 frequency deflection amplifies 50 times or sometimes 100 times if for a low damping case, which means that if you operate close to the resonance region, the amplitude of vibration can be enormous. Okay. And the dynamic magnification factor actually represents how the magnitude of deflection at 0 frequency gets amplified or magnified if the frequency of excitation approaches natural frequency. Okay. What you can also observe is that as the damping value increases, the peak response value keeps on reducing. So, for a value of zeta equal to 0.15, if the peak amplitude was 3 point, let us say 7 or 8, for a damping value of 0.25, the amplitude drops almost more than 50% and it drops to 2.1 or so, right. So, the damping definitely has a pronounced effect on the amplitude, peak amplitude at resonance. So, therefore, as you may all be aware that if I want to negotiate crossing through resonance for a vibratory system, then a larger damping will definitely be very helpful for me, right. For example, if I am operating at a frequency omega which is maybe 2.7 times 2.7 times the natural frequency of the system, or even maybe 3 times the natural frequency of the system, I will have to go from 0 to this frequency and I will eventually encounter resonance. And so, if I have a higher damping in the system, the amplitude of vibration at resonance can be controlled or minimized. Okay. In practice, this dynamic magnification factor, if it is less than 10, in general this number is not a sacrosanct number as such, but as long as this ratio is less than 10, preferably less than 8 or maybe close to 5 or so, even less, it is considered to be a good design in terms of avoidance of resonant amplitudes. And so, one has to calibrate the damping in the system, so that we get a reasonably low level of resonant vibrations. But at the same time, as we shall see in more detail later in this particular topic of forced vibration, arbitrary increase in the damping value is something can become counterproductive, right. So, we must not use damping as much as we want, but should be very carefully calibrated and chosen bare minimum. I mean bare minimum in the sense you can go for a larger damping, but just enough to take care of these resonant amplitude, because later on you will realize lesser the damping better it is. Particularly just to highlight that point, of course, in a different context we will learn it little better, but once you cross this resonance, let us say from this point onwards, just have a look at the advantage that you are going to gain by increasing the damping, hardly any, right. So, as long as you are working away from resonance, you really do not gain anything. The effect of damping will only be useful and helpful in the resonance region, where generally we do not operate for a long period of time. Okay. So, that is one point to be noted with regard to the damping in the system. There is no doubt that damping is beneficial, but it must not be arbitrarily raised to a very high value. Okay. Okay. We have only seen what is happening to the amplitude curve, right. So, we have seen how the dynamic magnifier looks as it changes with the frequency ratio R. Let us have a look at how the phase angle changes, and therefore, the plot here shows for some chosen values of the damping ratio, how this phase angle change with respect to the forcing frequency R. So, you can see that the phase angle for a low level of damping. So, the damping that we are looking at is 0.05 or maybe 0.15, which was considered somewhere here for this case. So, at lower frequency range, that means less than the critical speed. Okay. So, omega equal to omega n is the resonance frequency, which we call as a critical speed, because that speed is critical in terms of its operation. So, at this part of the operation, the phase angle phi is close to or less than 45 degrees. Okay. So, for the values of the damping which we are going, let us say up to 0.15 or so, in the region below the critical speed, the angles are less than 45 degrees. So, it is, or in fact theoretically at the entire range from 0 to 1, the angles are less than 90 degrees. Okay. So, the phase angle is less than pi by 2 before resonance, and generally it is for a low damping case, it's less than 30, 40 or so. Okay. Small value. The moment it flips beyond that, that means once it crosses this resonance point, the phase angle now is going to be approaching a value equal to 180 degrees. That means the value of phase angle phi will approach 180 degrees. It crosses through this angle 90 degrees irrespective of the damping, which you can find out from this expression. When R is equal to 1, no matter what the damping is, the angle phi is going to be 90 degrees. Okay. So, all the graphs cross through this point 90 degrees, and then they will approach a value of 180 degrees. So, the phase angle for small damping ratios is going to be either close to 0, okay, either close to 0 or it is close to 180 degrees. And all the graphs pass through this 90 degree, which means that the phase angle is going to be pi by 2 at r equal to 1, irrespective of the damping value, So, sometimes we may use the phase angle information for locating the exact resonance point, okay, which may sometimes be difficult because it is hard to get the exact peak point to locate the position of the natural frequency. Okay. But even the practical measurement of the phase angle can be challenging, but that is the point that we have for here. Okay, couple of things before we get down to the relationship between force and response is that at resonance all of us are aware that if there is no damping, this peak value can rise up to a very large value, and that is what we say resonance is the operation where amplitudes reach to infinite amplitudes theoretically at resonance. So, this is the total response that I talked about, comprising of this part which is the transient part and this part which is basically the steady state response at a particular excitation frequency omega. Now, if you solve this for the case at resonance wherein omega is equal to omega n or r, which is the ratio of these two frequencies is equal to 1, that is what we say the condition of resonance. Particularly for undamped case, the denominator will become 0 for this case and the solution actually is not defined actually. So, if we apply L'Hospital's rule in this case and take the limits and get an appropriate theoretical expression for the steady state part, that turns out to be this. We will not get into the details of that, but this particular part of the total solution has time as a variable, as a multiplier here, which actually indicates that the amplitudes actually strictly speaking builds up over a period of time at resonance. So, if you excite the system with a frequency of excitation omega equal to omega n, the response grows with time because the t is appearing here. So, as time t increases, the steady state part rises and then becomes larger and larger as time progresses. So, the response actually builds up like this, it does not go instantaneously to very high amplitude. The other thing that one should understand and note here is that, have you seen that kind of an amplitude building in a practical system? In practical system, the amplitude really does not go to infinity, like you have the amplitudes of response which are even at resonance limited. Of course, it also is true that in practical system you will not have this kind of a case where the denominator is only 1 minus omega or omega n square, that will also have a factor which is damping. So, damping is neglected here. So, in the reality the denominator is going to be 1 minus omega over omega n square and plus you will have damping related term anyway. So, that will not let the amplitude to be theoretically infinite, it will be finite. Of course, the amplitude will still be much larger. So, coming back to the reality, the amplitudes when they grow beyond certain limit, one of our assumptions for which all these expressions are derived clearly getting violated. You know, you started with the assumption that the amplitudes are small enough, right, they are small, therefore, the relationship between the force and displacement is linear, right. Similarly, the case of damping, and so in realistic systems, once the amplitude cross a certain level, the linear relationship between the restoring force and the response or displacement is no more valid, it is not true, and therefore, this perpetual increase in the amplitude is is only in theoretical expressions. In practice, the amplitudes are contained, they become finite. That is one thing, because of the basic assumption with which all these expressions are derived are no more valid when the amplitude grows beyond a limit. The other thing is, most of our vibratory systems are contained in the sense that if you consider a gas turbine or a steam turbine rotors, which are vibratory systems which we discussed, they are always limited by the surrounding structures. Like in gas turbines, you will have a cylindrical stator around it, or there would be seals which are surrounding the shafts. So, there are containing structures, surrounding structures, which will again limit the growth of these vibrations. So, there will be some rubbing happening here, there will be impacting conditions. This amplitude will not practically go to infinite value. So, that way the amplitudes really do not reach infinite value in practice. However, it is also important to understand here that large amplitudes are going to be creating secondary problems or problems of failures of such high speed rotors. So, therefore, that particular understanding of what this resonance is should be clear, that indeed the amplitudes do grow a large value even if there is a limited damping, as you can see here. For example, if you really see x over xst in the case of resonance, even if there is a damping, so it is almost like 2 zeta r basically is going to be your expression at r is equal to 1. So, this is essentially going to be 1 over 2 zeta. So, now if the damping is, even if you consider damping to be 0. Let us say 0.5, how much will be the denominator here? It is going to be 0.1, okay. And that basically means that the amplitude or peak amplitude at resonance is going to be 10 times the 0 frequency deflection. So, this peak, instead of 3, it is going to reach to a value, let us say 10, okay. And so, therefore, the damping, even if it is small, is going to limit the peak amplitude of vibrations to a reasonable value, and some amount of damping being always there in the practical vibratory system, the amplitudes really do not reach to an infinite value. It is only for a theoretically 0 damping value that the amplitude do reach to an infinite value, and that also happens over a period of time as the amplitude starts rising with time. That is how this particular figure is showing. Okay, the summary of this lecture, we discussed how the response to harmonic external excitation can be obtained. We in the process discussed the significance of dynamic magnification factor, or which is also called amplification factor, exemplifying the amplification of the response at resonance or as frequency of excitation changes in the response of the vibratory system. The questions based on this lecture are listed here. Please try and attempt these. These are very simple, straightforward questions. The answers are given in the next slide.